Good morning. Today we're going over our practice exam 2, and this covers our last two chapters on ionic compounds and covalent compounds in preparation for taking the test. And do remember that you get 2 attempts at this, and you can watch this video to help you see what you got wrong, what you got right, and hopefully make sure you got everything right for the right reasons. So hopefully this will be very helpful. Let's get started. This first question is looking at which element is going to make an ion with a charge of -2. So you've got 6 valence electrons, and that means that you're going to make a charge of -2. If you just look on the periodic table, group 1, 2, 3, 4, 5, 6, everything here has 6 valence electrons and would make a charge of -2 if they made an ion. So we're looking for oxygen, sulfur, selenium, and so forth. And so the answer here is oxygen. Next, what happens when an atom donates an electron? For instance, sodium would like to get rid of an electron. Calcium would like to get rid of 2 electrons to get a positive 2 charge. Well, where does that electron go? That's the question. Well, it has to go to another atom, essentially. So if that is donated, it doesn't fuse with a proton to form a neutron. It doesn't pair with another electron to form covalent bonds. That would be what happens if an atom shares an electron. But if it's being donated, the atom doesn't want it, doesn't need a covalent bond. So it's going to be acquired by or picked up by another atom, which then becomes negatively charged ion because electrons have a negative charge. So negatively charged ions are anions. So it's acquired by another atom, which becomes an anion. What is the correct formula for strontium phosphide? So this is where we start getting into nomenclature, and as you're going to see, there's like 4 or 5 nomenclature questions on this exam, so make sure you're prepared. In this case, strontium phosphide, strontium is right here, it's in group 2, and phosphorus is right here, it's in group 5. So when they're talking about strontium phosphide, then you're talking about an ionic compound between main group element strontium and main group element phosphorus. And in order for that ionic compound to be neutral, we're going to have to pair 3 strontium ions with 2 phosphorus ions in order to fully cancel out charges here so that we'll have a neutral formula. So that has to be Sr3P2. What is the correct formula for potassium hydroxide? Same story, but now we've got an ionic compound which contains a polyatomic ion. So you hopefully have memorized that hydroxide is a polyatomic ion with OH with a minus charge. And you can check your periodic table to confirm that potassium is element number 19. It's in group 1, so it has a +1 charge. So between the 2 of those, the formula between potassium and hydroxide will just be KOH. Next, what is the correct formula for lead 4 nitrate? So again, naming ionic compounds, but in this case, we're naming an ionic compound that contains a transition metal or a post-transition metal, in this case, lead. So we've got lead 4, Pb, and that little 4 means that it has a charge of +4. And nitrate is one of your polyatomic ions that you memorize. It has a charge of -1 and a formula of NO3. So if I put those together, I'm going to need 4 nitrate ions in order to cancel the charge from the lead ion. So it's going to be PbNO3 4. Next, this is a bit of a logic puzzle, but you know you have a compound that has XCl2. And they want to know what is X. And that includes knowing what the symbol is, but also what the charge is. So the first thing you could do is say, you know chlorine's in group 7, so it has a charge of -1, and there are 2 of them, which means that in order for this to be a balanced formula between X and chlorine, then that one X has to have a charge of +2. So we've already determined that X has a charge of +2, just based on the formula it makes with chlorine. Now we know that the ion, this ion, contains 20 electrons. So what is the identity of X? Well, we know that on the periodic table, our elements, if they're neutral, will have the same number of protons as electrons. So if we look at X plus 2 and we say that the ion has 20 electrons, and as a positive 2, that means that this element, this atom, must have lost 2 electrons in order to gain a plus 2 charge. That means that originally element X has 22 electrons. So that would be titanium. Titanium 2 plus would have 20 electrons. So the answer is titanium 2 plus. Next, question 7. This makes you put together all of your nomenclature information because you have to either name all of these and then compare them to the names that were given, or come up with formulas for all of these and then compare them to the formulas that were given and figure out which one is not correct. All right, so I'm going to name these ones because I think that's going to be easier than putting it together. So NH4Cr2O7, NH4 plus is the ammonium polyatomic ion. Cr2O7 is the dichromate polyatomic ion. And when we name ionic compounds with polyatomic ions, we just name those polyatomic ions. So that really is just ammonium dichromate. And yes, that's what they include here. For ZrCN2, I have one Zr, that is zirconium. And zirconium is, let's see, according to my periodic table, zirconium is a transition metal right here. So I'm going to have to include the charge there. So zirconium, in parentheses, is going to have a charge. And then this is our polyatomic ion cyanide. And cyanide has a charge of -1. So there are 2 cyanides, each at -1. That means that the zirconium must be a +2. So that is zirconium 2 cyanide. And sure enough, that is the name that they gave it. So that one is valid. Next, we have CaSO4. And if we look at CaSO4, calcium is a main group, so we just name it calcium. We don't need parentheses or anything like that. SO4 is a polyatomic ion that we memorized, sulfate, so it's just the name of that polyatomic ion, calcium sulfate. That is indeed the name that they give. Next, Ni2O. Nickel is a transition metal. It's right here, so we have to include the charge. We don't know it, but we can deduce it based on what we know, that oxygen has a -2 charge in an ionic compound. So this is going to be oxide, and because there are 2 nickels, then they each would have to have a +1 charge. So this is going to be nickel 1 oxide. And we look at the name, they called it nickel 2 oxide, so that one would not be correct. Finally, let's just check magnesium chloride, MgCl2. Magnesium is main group, so we just name it magnesium. Chlorine is main group, so we just name it chloride. And sure enough, that's the name they give. So nickel 2 oxide is incorrect. That should be named nickel 1 oxide. Or the formula for nickel 2 oxide would just be NiO, because in that case you'd have +2 from the nickel and a -2 from the oxygen. So that's the one we're looking for. Okay, next question. Main group elements that are metals usually do what with their electrons to form what, which have what kind of a charge? So main group elements, which are metals, here's a representative main group metal element, is sodium. Usually donates its electrons, so it can have fewer electrons, so it could be like neon. When it donates electrons, it loses a negative charge, and so it becomes a positive ion. So we call that a cation. Main group elements are metals that usually lose electrons to form cations, which have a positive charge. There we go. Naming this compound Mg3PO42. Mg is a main group, so you just name it magnesium. PO4 is a polyatomic, so it's just phosphate, you just name that. And we're looking at that one right there. Just as a reminder, for all of these nomenclature questions, you were looking at the nomenclature of ionic compounds lecture, and at the very end you've got this little table that should help you. If it's a main group, cation, anion, it tells you what to do. If it's polyatomic, it tells you what to do. If it's a transition metal, it tells you what to do. So the key is just to recognize, first of all, that it's ionic compound, so it follows these naming rules. And then second of all, what type of cation you have, what type of anion you have, and then follow those naming rules. If you can do that, you'll be great. One more here. What is the name of SnCl2? So this is another ionic compound because tin is a metal, and tin is a post-transitional metal because it is right here. So we're going to name it just like the transition metals. We know that each chlorine is -1 because they are in group 7, and there are 2 of them, which means that that one tin needs to be +2. So this is going to be tin 2 chloride right there. All right, which of the following compounds contains one or more covalent bonds? Now we know that ionic compounds form ionic bonds, and molecular compounds or covalent compounds form covalent bonds. So what you're looking for is one of these which has only nonmetals, because ionic compounds form between metals and nonmetals, and covalent compounds form between nonmetals. So barium is a metal, sodium is a metal, cesium is a metal, calcium is a metal, carbon is a nonmetal. This is the only one where carbon and oxygen are both nonmetals, therefore you're going to have covalent bonds instead of ionic bonds. Which of these contains a triple bond versus which of these contains a double bond? So this is how I'm going to ask you Lewis dot structure questions on the exam, because I can't have you draw in this multiple choice format. So instead, I'm just going to ask you questions about something that you should be drawing on your scratch paper, and hopefully that's going to work for us. So which of these has a triple bond? We have SO2. Sulfur comes in with 6. Each oxygen comes in with 6, and there are 2 of them, so I have a total of 18. We're following our rules for drawing Lewis dot structures. Sulfur is in the middle because it's listed first. We have 2 single bonds to oxygen atoms, so I've used up 4 electrons. That leaves me with 14, and now I distribute around exterior atoms, and each of those oxygens is going to need 6 more to make a full shell. That means I've used up 12. I've got 2 remaining. That goes on the sulfur. And then the sulfur only has 6 electrons. He wants 8, so I'm going to move those 2 electrons into the space between the oxygen and the sulfur, so sulfur sees 8. Now this is the right Lewis dot structure for SO2, and we see that we have a single bond and a double bond and a lone pair, but no triple bonds. All right, let's try CO. Carbon has 4 electrons. Oxygen has 6 electrons. We have a total of 10 electrons. Carbon is considered central, so we'll make 2 electrons in that bond, leaving us with 8. We distribute electrons on exterior atoms first. We've used up 6 more on that oxygen. We've got 2 remaining, so they go on that carbon. Then we see this carbon only has 4 and he wants 8, so we're going to move those 2 electrons to the space there, those 2 electrons to the space there. We can see that CO has a triple bond. Now if we continue on with these, we should see that CH4 has 4 single bonds. Carbon came in with 4 electrons. Each 4 hydrogen came in with 1 electron. So we've only got 8 electrons to distribute. And when I put in my 4 single bonds, I've used them all up. So that's what that is. And then for the NO3 minus, nitrogen came in with 5. I've got 3 oxygens. They each came in with 6. And then this means I have an extra electron. So I really have 24 electrons total. So nitrogen in the middle, used up 6. I have 18 remaining. 2, 4, 6 on that oxygen. 2, 4, 6 on that oxygen. 2, 4, 6 on that oxygen. And now I've used 18 and I have none remaining. So 2 of those electrons will have to be moved to the space between the oxygen and the nitrogen so the nitrogen can be full. And now we have nitrogen has 2 single bonds and a double bond, but no triple bonds. So the CO is definitely the right answer. For question 13, which of the following contains a double bond? We look at Cn minus. Carbon has 4 electrons, nitrogen has 5, and we have an extra electron because of the negative charge. Add that up to 10 electrons. Carbon is central. 2 electrons to bond that to the nitrogen, and then an additional 2, 4, 6 to fill in that nitrogen. So I've used up 8 of my 10. Got 2 remaining, those go on the carbon. And now I'm going to have to push those 2 sets of electrons in between the space between the nitrogen and the carbon. And that gets me a triple bond right there. So that's not a double bond, that's a triple bond. Let's try H2O, H2O. Each hydrogen comes in with 1 electron, an oxygen comes in with 6 electrons, so that is 8 electrons total. And then we see the O in the middle, 4 electrons. And then 5, 6, 7, 8, used up all 8 electrons. And oxygen has a full shell, so does each hydrogen. So we only have single bonds there. There are no double bonds. C2H2. I've got 2 carbon atoms. They each have 4 electrons, plus 2 hydrogens. They each have 1 electron. That's going to be 10 electrons total. Now in this case, my 2 carbon atoms are central, and then they're each attached to 1 hydrogen atom. And that will have used up 6 electrons. I have 4 remaining, and it doesn't matter which one you pick. Hydrogen atoms are full. We'll put the remaining 4 electrons on this carbon, and hopefully you'll see, oh, those are going to have to be moved into the space between the 2 carbon atoms so that this carbon atom on the right can be happy as well. So that's going to look like that. So that's got a triple bond. C2H4, each carbon comes in with 4 electrons. Each hydrogen comes in with 1 electron. So we've got a total of 12 electrons. 2 carbon atoms are central. We're going to distribute the hydrogens evenly across them. And we've used 2, 4, 6, 8, 10 electrons. We only have 2 left. If I put them on the left carbon, then the right carbon would not be happy. If I put them on the right carbon, then the left carbon would not be happy. So they're going to have to be shared between them. And hopefully you can see that now my C2H4 has a double bond. That's what they were asking about. All right, question 14. What does the chemical formula Al2O3 indicate? And that means we've got 2 atoms of aluminum and 3 atoms of oxygen. That's what that formula indicates. And for question 15, a chemical bond formed when 2 atoms share electrons, that is a covalent bond. And if you're sharing 2 pairs, then it is a double bond. So double bond, it is described as covalent because they're being shared. How would we name PCl3? Now, you have to here recognize that PCl3 is a covalent molecule and not an ionic molecule. So we're not going to use the naming rules that were on my ionic naming chart. Instead, we're going to use the naming rules that were on my covalent naming chart. And in those cases, we say the names of the elements. The last one ends in "ide," but then we also indicate how many there are with a prefix. So phosphorus, it would be monophosphorus, but we dropped the mono for the first one. And then we have 3 chlorine, so that becomes trichloride. So that is phosphorus trichloride. Question 17, consider the molecule SiCl4. We're given the electronegativity values, and we're not told what the molecular geometry is, but we're going to need to write that out. And they want to know what's the SiCl bond about and what is the molecule about. So just based on these electronegativity values, we see the difference is 1.2. So we know that the bond is polar. So we can narrow it down to this one or this one. So the bond is polar, and then the molecule will either be polar or nonpolar depending on what the geometric shape of that molecule is. So let's draw this molecule so we can get an idea of what's going on. We have SiCl4. Silicon is in group 4, so it has 4 electrons. I have 4 chlorine atoms. They each have 7 electrons. So I have a total of 32 electrons to deal with here. Now we have silicon in the middle, and I have 4 chlorines attached to it. So in the process of making those attachments, I have used up 8 electrons, and that leaves me with 24 electrons. And then we distribute electrons around the exterior atoms until each of them has a full shell. And since each chlorine atom has a single bond, they will each want 6 more electrons to get up to 8. So 4 chlorines at an additional 6 electrons each means we're using up all 24 electrons in order to fill that, and we're totally out. Then we look on the silicon, and the silicon is happy. It has 8 electrons because it has 4 single bonds. So when we evaluate that structure, everything looks good. That is the Lewis dot structure for silicon tetrachloride. And then we have to look at the geometry. So according to our VSEPR table, valence shell electron pair repulsion theory says that if I have 4 electron sets, as I do here, each single bond is an electron set, then that will have a tetrahedral electronic geometry. So since silicon has 4 electron sets, the geometry around silicon is tetrahedral, and I can redraw that like so. And I'm not so worried about the electrons surrounding the chlorine atoms. We're just looking at the silicon for the moment. And then we did determine that the bond was polar. So that means that we're going to look at something like partial negative on each chlorine, because each individual bond is polar. So negative on the chlorine, positive on the silicon, negative on the chlorine, positive on the silicon, negative on the chlorine, positive on the silicon, and so on and so forth. And hopefully when you do that, you'll see that all the outside elements are negative and the inside ones are positive. So it does not pass the line test. I cannot push the positives on one side of the molecule and the negatives on the other. So the molecule is not polar. Next, which element listed is the most electronegative? And we can just look this up at our table of electronegativity values, which is given to you on the test. So you don't have to memorize these. And we're looking at sodium, that's 0.9. Iodine is 2.5. Bromine is 2.8. Chlorine is 3.0. And aluminum is 1.5. So chlorine is the most electronegative of all of the elements listed there. Now, what do we know about water? They're asking us something about the bond angle and why it would have that bond angle. And bond angles have to do with geometric shape. So let's draw the geometric shape of water here. First of all, we have to do the Lewis dot structure. Water, H2O, has 2 hydrogens with 1 electron each, plus an oxygen with 6 electrons for a total of 8 electrons. Oxygen in the middle, 2 bonds to hydrogen, that uses up 4 electrons. I've got 4 remaining. Hydrogen atoms are full, so those 4 remaining electrons go on the oxygen, and I'm all out of electrons. I evaluate the structure, and the hydrogen atoms are full and the oxygen atom has 8, so that is happy. But if I look at my VSEPR shapes table, I see that I have 4 electron sets around that oxygen because I have 2 lone pairs and 2 single bonds, and each of those counts as an electron set. So the electronic geometry is tetrahedral around that oxygen. And the molecular geometry, which is looking at just the atoms involved, is bent. So what they're saying is the bond angle here is what? And for tetrahedral electronic and molecular geometry, we've got 109.5 degrees approximately. So approximately 109.5 degrees because the atom has 4 electron sets, tetrahedral electronic geometry. If it had 3, then that would be trigonal planar, that would be 120 degrees. And of course, if it only had 2, then it would be 180 degrees because it would be linear. So we're looking at this first answer right here. According to VSEPR theory, a molecule with 3 charge clouds or electron sets, including 1 lone pair, so we're looking at this one here, 3 charge clouds, and if we make one of those a lone pair, then we have an atom here and atoms here. So the shape or molecular geometry would be bent, just like that. Which of the following bonds is the most polar? We're going to have to look at our table of electronegativity values here. N, C, N is 3, C is 2.5, so that's a difference of 0.5. ClO, 3 and 3.5, that is also a difference of 0.5. C and H, 2.5 and 2.1, that's a difference of 0.4, that's even lower than these two. F and Cl, fluorine is 4, chlorine is 3, so that's a difference of 1, that's the highest we've seen so far. And OF, O is 3.5, fluorine is 4.0, and so the difference is 0.5. So FCl has the largest difference in electronegativity values, therefore it would be the most polar bond. Next, which of the following molecules is polar? So this is one where we have to draw out the molecule on the Lewis structure, then draw out the molecule with the correct VSEPR shape, and then apply bond polarity appropriately to see if the whole molecule is polar. Now, there are a few little shortcuts that we can do. For instance, if we look and see, our options are CO2, O2, SO3, NH3, and CH4. We can eliminate O2 because oxygen with oxygen has an electronegativity difference of 0. So no polar bonds means I can't be a polar molecule. And then for CH4, same story. We can look at these and see carbon is 2.5, hydrogen is 2.1, so that bond is not polar. Lacking any polar bonds, I cannot be a polar molecule, so I can eliminate that one as well. For NH3, I have a difference of 0.9, so those will have polar bonds. I better check to see if the molecule is polar. For SO3, difference of 1, again, that would be polar bonds, so I better check those because that could be a polar molecule. And for CO2, we have a difference of 1.0. Again, that could be polar. So I'm going to have to check these 3, but at least I don't have to check 5. That helps a little bit. So starting with CO2, I've got 4 electrons from the carbon plus 2 oxygen atoms at 6 each. That's going to be 12 plus 4 is 16 electrons. Carbon in the middle, 1 oxygen on the left, 1 oxygen on the right. I've used up 4 electrons. I have 12 remaining. Distribute those on the exterior atoms first until they have full shells. Since each oxygen will want 6 additional electrons, I will have used up all 12 and I'm all out of electrons. Then I evaluate the structure and see the carbon's not happy. I'm going to have to move those to the middle. And when I do that, I end up with 2 double bonds, 1 from each of the oxygen atoms to the carbon. Now that puts me at 2 electron sets. So the CO2 molecule really is linear as already shown. And since I know the bonds are polar, I can add those in. And hopefully you guys will see that this is not a polar molecule because it's like a tug of war, equal and opposite directions, and no one side gets a preponderance of the negative charges or the preponderance of the positive charges. Can't pass the line test. So this is not polar. Next, SO3. Sulfur comes in with 6 electrons. Each oxygen comes in with 6, and there's 3 of those. So that gives me a total of 24 electrons. Put sulfur in the middle, oxygen, oxygen, oxygen. I've used up 6 electrons. I have 18 remaining, and I distribute electrons on exterior atoms first until they have a full shell. And because each oxygen will want 6 more, that's going to be a total of 18 electrons, and I'm all out of electrons. And then I evaluate the structure and see the sulfur would like 2 more electrons. So I'm going to move those 2 electrons in, and when I do that, it's going to look like that. And then for the VSEPR shape, I see I have 1, 2, 3 electron sets, so it's actually going to be trigonal planar, and I need to be able to draw that as a triangle in the plane. And I know that each bond is polar, so positive on each sulfur and negative on each oxygen for each of those bonds. And hopefully you'll see the outside atoms are negative, the inside is positive. So this is not polar molecule because I don't have one side with a positive pole, one side with a negative pole. All right, final one, we've got NH3. Nitrogen comes in with 5. I have 3 hydrogens, they each come in with 1. So I have a total of 8 electrons. And if I put 3 hydrogens on nitrogen, I will use 2, 4, 6, and those last 2 are going to go in the nitrogen because the hydrogen atoms are full. So I have used up all 8 electrons. When I evaluate it, I see that nitrogen has 8, each hydrogen has 2, that's happy. And for the correct VSEPR shape, I see I have 4 electron sets, and one of them is a lone pair. So I am tetrahedral electronic geometry and trigonal pyramidal molecular geometry. So it looks like that. And then I do know that these bonds are polar, so each hydrogen, so the nitrogen gets a negative charge and hydrogen gets a partial positive charge, and that's true of each bond. Partial negative on the nitrogen, partial positive on the hydrogen. And when I do that, the hydrogen atoms will end up with partial positives on that side of the molecule. Nitrogen atom ends up with partial negative on this side of the molecule. So that is in fact a polar molecule. And that is a bit of a long and involved problem. That's probably the longest and most involved problem that you're going to have. But there's not really any shortcuts other than eliminating the ones that don't have polar bonds at the beginning. All right, next, which of the following cannot have hydrogen bonds? Remember, hydrogen bonding is a type of intermolecular force where the hydrogen is bound directly to a fluorine, an oxygen, or a nitrogen, because hydrogen bonding is fun. So if I don't have a hydrogen, and if I don't have one of these, then I definitely cannot have hydrogen bonds. So in this case, and you could draw each of these out if you needed to, but this one right here doesn't even have a fluorine, oxygen, or nitrogen. So it cannot be subject to hydrogen bonding because there is no hydrogen directly attached to a fluorine, oxygen, or nitrogen. Each of these other ones, fluorine, nitrogen, nitrogen, oxygen. And which of these has the highest melting temperature? This goes back to intermolecular forces. The stronger the intermolecular forces, the higher the melting temperature. We saw that London dispersion were the lowest, followed by dipole-dipole, followed by hydrogen bonding, and the highest that we saw were ionic bonding. So if we see an ionic compound, that would definitely be the highest, and London dispersion forces would definitely be the lowest. Hopefully you can see here, this is an ionic compound. So that's going to be the very highest because magnesium's a metal, fluorine's a nonmetal. That's going to be ionic bonding. And finally, which intermolecular force is characteristic of compounds with a low molar mass, which are liquids at room temperature and have relatively high boiling points? So since something like boiling point is going to scale with molar mass, then to have a high boiling point with a low molar mass means you're going to have relatively strong intermolecular forces. So a good example of this is water, because water is a liquid at room temperature. It has a boiling point of 100 degrees Celsius, despite the fact that it has a really low molar mass, only 18 if you add up the mass of hydrogens and oxygen. So when you compare that to other elements or other compounds, for instance, if you have gaseous nitrogen that we breathe, N2, it weighs 28 atomic mass units. Carbon dioxide, same thing, we breathe, it's a gas at room temperature, and it has 44 atomic mass units, whereas water, very small, very light, only 18, but it is a liquid at room temperature, and that's because it is experiencing relatively strong intermolecular forces. And so it's not going to be London, it's not going to be ionic. Ionic bonds would be solids at room temperature. Salt is your really good example of a solid. Covalent bonds is not a type of intermolecular force, although it would accurately describe the type of bonding inside the molecule that has this type of intermolecular force. What you are looking for is hydrogen bonds. And finally, most metals are solid at room temperature. So you can go through here and say, okay, ionics are solid at room temperature because you know, for instance, salt is solid. Metallics are solid at room temperature because you know that, for instance, gold is solid. You know that covalent bonds are not a type of intermolecular forces. So if you choose between London forces and hydrogen bonds, you would see hydrogen bonds because they have relatively high boiling points compared to the other stuff there. Okay, that is it. I hope this was helpful, guys. Have a great day and good luck on your test.